Hello, today we are going to be talking about machines. By the end of today's class, you should be able to define machine, explain the terminologies used in machine, which includes mechanical advantage, velocity ratio, and efficiency. Okay, now we'll start with machine. What is machine? Machine is simply anything, any device that can make our work easier or simple to do. Okay, is a force producing device that is used to overcome large load with what? Small efforts. Okay, large load to overcome anything that is able to what? Overcome large load with what? Just a little effort. Okay, now we are going to talk about mechanical advantage. All right, what is mechanical advantage? Mechanical advantage is simply the ratio of load to effort. The ratio of what? Load to effort. Okay, now mechanical advantage is denoted MA, and the formula is load all over effort. Load all over effort, and the load is denoted with capital letter L, and the effort is denoted with capital letter E. Okay, let's just put L. This is equal to what? It's denoted with capital letter L. Effort is denoted with what? Capital letter E. What is load? Load is simply the resistance that is overcome by the machine, while effort is the force that's applied into the machine. Okay, for instance now, okay, if we have a wheelbarrow man pushing a bag of rice, okay, the effort is applying into the machine on the handles of the wheelbarrow, okay, pushing it. That is the effort. Now the bag of rice is the load to be overcome by the wheelbarrow pusher, okay, by applying his own effort. Are you here? So that is mechanical advantage. So it means that mechanical advantage can be defined as what? Ability to what? Overcome a large load with small effort. Why do you think that it is called mechanical advantage? For you to be at an advantage, it means the effort really needs to be very small. Okay, the advantage will be more when the effort is smaller. Okay, let's take this as an example. Let's say the load, we have load over effort. If the load is 8 Newton and the effort is, let's say you are applying 4 Newton effort, what will be your mechanical advantage? It will be 2. Now let's reduce the effort. Let's reduce the effort to 1, to the lowest minimum. You will have load over effort is equal to 8 over 1. What do we have as our mechanical advantage? It's going to be 8. So the mechanical advantage, or it is more advantageous when the effort is at minimum. Are you here? So the lower the effort, the more advantage it is. So now let's talk about the velocity ratio. What is velocity ratio? Okay, what is velocity ratio? Velocity ratio is simply denoted with VR and is defined as the distance moved by effort, the ratio of the distance moved by effort to what? Distance moved by load. So is equal to what? Distance moved by efforts all over distance moved by load. Okay, unlike mechanical advantage, the load there is denoted with capital letter L, while the effort is denoted with capital letter E. Now here in velocity ratio, distance moved by effort is denoted with small letter E. Okay, while distance moved by load is denoted with small letter L. And of course, mechanical advantage has no unit because it is force ratio. So when you have force ratio, it means force over force. Newton will cancel Newton, and you have no unit. This one also velocity ratio, okay, is a ratio of the distance between two forces. Okay, so the unit will cancel out. Velocity ratio has no unit too. Now efficiency. Efficiency is denoted with this symbol. I don't know what the name is, but it's denoted with this symbol. Okay, like the inverse of 3. I don't know how to put it. Okay, now the efficiency is simply it gives us the relationship between mechanical advantage, velocity ratio, and efficiency. Okay, from the formula. For us, the formula for efficiency. Okay, there is no machine that is 100% efficient, and that's because of what? The friction between the moving parts. Okay, now we will talk about the relationship between mechanical advantage, velocity ratio, and efficiency. Okay, now we have this E is equal to work output all over work input times 100%. Work output all over work input times 100%. But we know the formula for work. Work, but work is equal to force times distance. Work is equal to what? Force times what? Distance. Now in machine, we see force to be what? Load. We see force to be what? Load. And we also see force to be what? Effort. Are you here? So now in machine, this force can either be measured in Newton or in kilogram. So if you see kilogram, you shouldn't be confused. Okay, in machine, we refer to load and effort as force. Sometimes you'll be seeing mass. We also regard mass as force. Okay, so now let's continue our derivation. Work output is all over me. Work input times 100%. So we have from there now we have this. Okay, work output becomes force times distance moved by load. All over force times distance moved by efforts times 100%. Times 100%. Now we have this. Distance moved by load. Sorry, it's small letter. Okay, yeah, load. Effort, correct. Now, F, we have E is equal to this times this is going to be load. Effort times distance moved by effort. Load. Let's use the machine terminology. I told you that force is seen as load and effort. So for this now, our force will be load for what? Output. And our effort will be the force for what? Input, work input. For this place, the load will be what? The force for work output. So we still have our force times distance, force times distance. Okay? So we have load. This distance moved by load is denoted with small letter L. Then we have this E times distance moved by what? Effort is denoted with letter E. Okay? Times 100%, please. Okay, so we have this. We can say we have L all over E, okay, times L all over E times 100%. But mind you, if you still remember, the formula for velocity ratio, we have VR is equal to what? E over L. That's distance moved by effort all over distance moved by what? Load. Okay, distance moved by effort all over distance moved by load. So now we want to suit what we have here. Okay, we have L of E, that's the inverse of this. So it means our 1 over VR will be equal to what? L over E. So we'll substitute this into this. So if we put this inverse now, it will now be 1 over VR instead of LE. So let's do this. So we have E is equal to L over E times 1 over VR times 100%. Is that okay? So this becomes E becomes what? L over E, okay? Aha! L over E, you know we know that MA is what? Load over effort. So we substitute this here, L over E. So E becomes what? MA times what? 1 over VR times 100%. Okay? So if we multiply, we have this times this, we have what? MA all over what? VR times what? 100%. And this is the relationship between efficiency, mechanical advantage, and velocity ratio. Where E is efficiency in percentage, mechanical advantage, velocity ratio. Okay? Now, before we go into problem solving, we are going to talk about the simplest form of machine. And the simplest form of machine is what we call the lever. The lever. Is it lever or lever? Lever or lever? Lever. Is it lever or lever? Oh. Let me call it lever. It's the simplest form of machine, okay? Now, a lever, there are 3 classes. There are 3 classes when it comes to lever. And usually I tell my students you can easily identify or differentiate between the 3 classes by simply writing flare. What did I say? Flare. Flare. This is it. Flare. This one goes for first class. This one goes for second class lever. And this one goes for what? Third class. By now you should be able to understand what I mean. Now, in the first class, the fulcrum is between the load and the effort. This is the drawing. The fulcrum is between the what? The load and the what? The effort. The fulcrum is between the load and the effort. Then for second class, the load. This is the load. Is between the fulcrum and the efforts. Anyhow you want to draw, you can draw the 2 sides in the same direction. Doesn't mean. Now we have the third class. The efforts is between, okay, the fulcrum and the load. Okay, you can see flare. Okay, for first class lever, the fulcrum is between the load and the effort. For the second class, the load is between the fulcrum and the effort. And for the third class, we'll have the effort between the fulcrum and the load. These are the 3 classes of lever. Okay, for the first class, an example is the scissors and the seesaw. Okay, If you have, I don't think I can draw a scissors, but let me try. I don't know if I can draw a scissors. I don't know. I'm not sure. Please don't laugh. I don't know if I can draw a scissors. I'm not sure. Please don't laugh. Please don't laugh. Now, let's say this is a scissors. This point, this is the fulcrum. This is the fulcrum. This is where you put the cloth or whatever you want to cut. And this is where the effort will be applied. Okay? Usually the fulcrum is the turning point. Okay? Now we have, this is the fulcrum, and this is the load, and this is the effort. What class does it belong to? Fulcrum between the load and the effort is first class. Okay? This is first class lever. It's under the first. It's an example of first class lever. Then the second class, we have examples like the nutcracker. Then we have the third class, we have the bicep of the arm. Okay? Now, we want to solve problems on machine. In the next class, we will talk about momentum force, couple, and every other thing. Thank you for watching. I'm still Bukola Joseph.